Investigating the possible benefit of heightening 29er foils to the average VMG of the 29er. Principles of hydrodynamics govern sailing, and the outcome of competitions through their details are often neglected. It is typical for the best sailor to maintain the best VMG through skill and technique, but an understanding of hydrodynamic principles can allow for competition gains. As stated by the International 29er Class Association boat specs, the 29er is a 4.4 meter long skiff boat made of glass reinforced polyester, or fiberglass, which weighs 90 kilograms, and has a total sail area of 30.02 square meters. Designed as a youth boat, the ideal combined skipper and crew weight is 120 to 140 kilograms. Although the typical youth race boats are Optimist or Club 420 dinghies, the concepts of the typical dinghy boats are completely altered in the 29er, which is a skiff boat that is comparatively lighter and smaller, with power based low in the main and jib sails, allowing for less overall drag and a more effective riding moment to aid sailors in heavy wind speeds. The foils on a 29er came about in typical experimentation fashion, trial and error. In a study comparing the various angles of attack, square, cosine, sawtooth, and modified, the modified angle of attack, the shape most similar to the foil on a 29er, had the greatest acceleration and maneuverability. Its water flows around the foil from the leading to the trailing edge in a fashion providing for greater propulsion through the water and generation of speed, generating hydrodynamic forces. The purpose of the foil is to resist side load generated by the sails. The foil design of the 29er does this by allowing yaw, meaning the boat slips to leeward at approximately 1 to 2 degrees. The 29er's yaw, as a result of the foil's depth, width, and shape. That being said, it is safe to say that the dimensions of the 29er are at the best possible shape for maximum speed, as it prevents the boat from sliding sideways and provides a shape for proper acceleration and maneuverability. A document written by the International 29er Class Association points out that the foils must prevent side resistance to maintain forward motion of the 29er. With the 29er being so shallow, there is little side resistance, and 10% of the side load is on the rudder and 90% is carried on the centerboard. The riding moment also aids in forward motion maintenance. As analyzed in a document by Finley and Turnick, riding moment can be described as the moment that the skipper and crew are both extending themselves, windward helm, in the opposite direction of the sail force to keep the boat from rolling over. At this moment, the driver and crew are trying to counteract the center of gravity and center of lateral resistance so that the boat does not roll over, which occurs if the driving force exceeds the riding moment. As the riding moment is reduced, the foils generate lift, increasing the intensity of the side load that the foil has to resist, causing the hull to slide sideways. Increasing weight over the rail by lowering the crew on the 29er trapeze wire can increase the riding moment by reducing the distance between the center of effort and center of lateral resistance, making an effective riding moment. When the trapeze is lowered all the way, the next solution to excess driving force can be raising the foil, which raises the center of lateral resistance and decreases the distance between the center of effort and center of lateral resistance. When the driving force exceeds the riding moment, instability results and it becomes hard to steer as vertical depth of the foil decreases. Mark Chisnell, member of America's Cup Team BAR, says that establishing stability only requires an adjustment in the angle of attack of the foil. This is done by raising the foil and can be seen in the America's Cup on foiling catamarans as well, which use manipulation of the angle attack to remain on the foils where they are the fastest. In the 29er, this yaw angle should be 2 degrees. The greater the riding moments in a hull are, the greater the speed is likely to be, and as a very light boat, the 29er has a very large riding moment, so greater speed potential. With greater speeds come greater stability, which is why the riding moment is also referred to as the stability moment. To determine the angle of heel at which the righting moment is most effective, the following equation can be used. MW equals 0.75 V squared W times A times S times parentheses HCE plus HLP and parentheses times parentheses cosine theta parentheses 1, 3, 4, with VW being the wind speed in meters per second, A times S being the projected sail area in meters square, HCE being the center of gravity of the sail above the waterline in meters, HLP being the center of the surface area below the waterline in meters, and theta being the lateral heel angle in degrees. It is important to sail the hull at the angle of least sideways resistance consistently for maximum speed and stability. Sailing consistently at this angle while maintaining maximum speed requires proper flow over the sail, which can result in an inefficient righting moment if not properly ensured. Raising the centerboard raises the center of lateral resistance half this amount and decreases the distance between the center of effort and the center of lateral resistance, which also increases the effectiveness of the righting moment. This balances the center of lateral resistance and center of effort, and in combination with proper flow allows for speed maximization. Lift is a force that reduces drag created by the interaction between the water and the boat through an inverse relationship, and it is correlated with speed. The two types of flow around the foils in the water are laminar and turbulent flow. Laminar flow occurs at low velocities and is characterized by the smooth sliding of adjacent layers. Turbulent flow occurs at higher velocities and is the curling of field lines and mixing of adjacent lines. Perturbation analysis determines the type of flow by using the critical Reynolds number, which includes viscosity, density, critical velocity, and boundary conditions. If the critical Reynolds number is equivalent to the constant with condition y, decay of perturbation, equals 0, you are at the transitional point between the two types of flow. It is at this point you want to raise the foil because you will always be increasing you always want to be increasing turbulent flow for greater lift and in turn marginal increase in velocity. For planing boats, the lift coefficient is on average the highest when the angle attack is 15 degrees. The lift coefficient is gained through the Reynolds number, and the greater it is, the more turbulent flow is present, increasing lift and speed. Using a proper angle of attack, which is 2 degrees in the 29er, and the equivalent of 15 degrees in the model provided, generates lift. Lift can be increased in skiff boats, such as the 29er, by moving the center of gravity forward at low speeds through physical weight movement. At high speeds, moving the center of gravity aft lifts the bow out of the boat out of the water, which also increases lift through decreased drag caused by friction. The generation of lift is key to the overall speed of the 29er skiff boat, so understanding how it is generated and altered is important to maximizing speed. Drag is the opposing force of lift, which slows the boat down, decreasing VMG. The overall drag acting on a skiff hull is comprised of spray drag, induced drag, and frictional drag. Frictional drag is typical at low speeds and is the result of water displaced by the hull. At a certain speed through the water, the amount of lift generated by the blades peaks and decreases with any extra speed being drag. This is because a smaller portion of the foil is required to create the maximum amount of lift, so any extra foil length in contact with the water is unnecessary and therefore causing drag. To reduce this drag, you can raise the foil, reducing the amount of the foil in the water, and therefore wet its surface. In a scholarly peer-reviewed journal, equations using a GA method calculated what variables affect the total resistance, or drag, of a boat. The results indicated that the greatest decrease in drag resulted from changes in trim angle. Therefore, drag can be reduced by adjusting trim angle through foil height. Methods. The method used was a quasi-experimental design to identify a cause and effect relationship. All factors that could possibly affect the dependent variable VMG include sailing technique, wind speed, wind direction, current, and waves. To maintain internal validity of this experiment and yield a legitimate conclusion regarding the cause and effect relationship between foil height and VMG, a control group and constants were included. With wind speed was being held constant by ensuring the trials for each board height took place within the specified wind range. Wind direction was similarly held constant by ensuring the wind direction did not deviate greater than 20 degrees throughout the trials within a speed range, and using the same wind direction for the trials in a breeze range to determine VMG. Current and waves were held constant by sailing in the same place for the same amount of time in each trial within a wind speed range. The trial started at the Tampa Bay channel marker FLG4S, coordinate 27 degrees, 45.985 degrees north, 36.586 degrees west, and then involved sailing for 2 minutes on starboard before tacking and sailing for another 2 minutes on port. Sailing technique was held constant by following the Julian Bethwaite rigging and coaching manual and by sailing with the same crew for each trial of each breeze range. The control group for each wind speed range was a height of 0 millimeters. On to boat setup. The International 29er class has specific requirements regarding the sizes and weights of various 29er boat parts. The 29er hull used for the test had met all these specifications, weighing 74.9 kilograms and having a forestay length of 0.50 millimeters from the specified measurement point. All other mass specifications were within proper range as created by the factory producers. The foils must similarly meet 29er class specifications, and the foils used measure within range. The sails, the jib, spinnaker, and main must meet international class requirements as well. The sails used were manufactured by McDermott Sails. When rigging, it is important to ensure the only inhibitors of maximum VMG are sailing ability and not setup. To ensure proper setup for each breeze range, refer to Julian Bethwaite's rigging manual. The centerboard. This is what keeps the boat from moving sideways. It is inserted through a slot in the middle of the boat, and it is what we will be raising. On to deciding test time. Testing in various breeze ranges is crucial to determining the benefit of raising foils. It is important to begin raising the foil as turbulent flow is established around the foils and when the wind speed is at a greater range. This flow is established earlier than lesser breeze ranges, meaning that the foil is raised at different times in varying breezes. The breeze ranges are each independent of each other. It is typical for a standard weather day to have little variance in wind speed, so the experiment happened over the course of 2 months to ensure tests in various breeze ranges. Weather prediction programs on the National Oceanic Air and Aviation website, Wind Alert, and WeatherBug were used to predict the breeze range for upcoming days. If the prediction was within or close to a breeze range, tests were required to be completed in. The crew was contacted and notified of the test time and date. Upon arrival to the sailing center, an anemometer had been used to take 5-minute wind averages and determine the wind speed. If the wind speed was within one of the untested breeze range trials for that breeze range, no trials would be conducted, trials would be conducted. Once out to the sailing area on Tampa Bay, the anemometer was once again used to take a 5-minute wind average and clarify that the wind speed was still within the specified wind range. For deciding testing location, VMG can be affected by shifts in wind direction, wind speed, and current. To restrict these confounding variables, testing in the same area for each breeze range was necessary. The chosen area of sailing began at the FLG4 marker in Tampa Bay, approximately a mile due east of the St. Petersburg Yacht Club. After clarifying the breeze range testing would take place in, a compass had been used to determine the wind direction. Testing would not continue if the wind direction deviated more than 20 degrees from the original breeze direction. This wind direction range had been chosen because it is typical for a professional race committee to end a race or adjust the race course if there is a shift in wind direction greater than 20 degrees. For performing the trials, before beginning the trials for each breeze range, the Velocitech would be turned on and the time marked that the boat began sailing into the wind, close-hauled on starboard. The first 3 trials started at a centerboard height of 0 millimeters. The trial started by rounding the leeward side of the channel marker, leaving it to starboard. The boat was then sailed into the wind for 2 minutes, tacked, turning the boat into the wind and continuing past this point to the close-hauled point on the starboard side. Sailing continued on port for 2 minutes. After marking the time the trial was completed, the step was repeated an additional 2 times from the same starting point for a total of 3 trials at that foil height. After having completed 3 trials at that height, the experiment continued for this breeze range by performing 3 trials at the following heights: 150 millimeters, 250 millimeters, 350 millimeters, and 450 millimeters. For testing VMG, the Velocitech used tracks and speed and compass heading. The speed and compass heading for each trial was then inputted into a program called My Velocitech. This program calculated the average VMG for each trial using the speed and compass headings collected on the Velocitech, as well as the breeze direction for each breeze range used. The average VMG of the 3 trials for each board height was calculated and then compared to the average VMG of the 3 trials for each of the other foil heights. Now for final results and findings. It is hard to determine any correlational relationship between board height and VMG in the raw data due to many variances in VMG. A table is next given showing the average VMG for each board height and each wind range, and trends are going to be discussed. I am comparing the change in average VMG between a height of 0 and each board height because a board height of 0 millimeters is how the boat is typically sailed. A height of 0 millimeters is the control group. The VMGs will also have smaller or larger increases and decreases in VMG with each sequential board height. So the best way to tell how beneficial a change in board height can be is by comparing these VMGs to the VMGs with a height of 0 millimeters. I cannot discuss anything with standard deviation or anything related to a histogram or frequency because I am dealing with a variable that did not involve human interaction or proportions involving the amount of time something occurred. There are 2 variables and I am looking at the VMGs for each. I will be providing the correlation value R because I can use this to show a general trend. The data is discrete and the scale is neither nominal, ordinal, interval, or ratio. I am only going to look at correlation briefly. Essentially, that's it. Okay. And ta-da.